Good morning, guys. Today we're going to wrap up our unit on just general basic probability by talking about conditional probability and independence. What is conditional probability? Well, conditional probability, as you might think, is a probability with a condition put on it. So it's the probability of one event occurring, assuming that another event has already occurred or a condition has been met. So from a notation standpoint, you'll see it written like this. Now, these two little symbols here, this is a vertical bar. Right, that's, we just say given. When you see that vertical bar, you're going to read that as given. So this says probability of A given B. So that's the way we would interpret that. The probability of event A given that event B has already occurred. So if you'll read it that way, it becomes pretty obvious what it's saying. It's saying that B has happened and it has changed our probabilities. Now we've got to look at the impact of that change on A. That's what we're talking about with conditional probabilities. Now, we can calculate that a couple of different ways. One is if we have a two-way table set up, we just look at the column or the row that meets that condition and then calculate your possible, your successes out of your possible for just that one column or just that one row. If we don't have that individual information, we can just look at A and B separately, or the probabilities for A and B separately, and then combine them together using this formula. So we get probability of A. Now, if you'll remember from the last section, that little hump right there, that is the intersect symbol. So probability of A intersect B. Or we could also say probability of A and B. The probability that both of them were occurring at the same time, and we divide that by the probability of B. Now again, that should be an intuitive thing from a two-way table because B is our condition, so your possible is just your B's, so whatever's happening in that row or column, and then this is the intersection of the A column and the B column. So that's how that works fitting with the two-way table definition. But again, we can work it from A and B separately information. So we have a couple of examples here. What's the probability that the temperature will drop drastically if it rains tonight? So what we have here is a Venn diagram of temperature dropping and rain. So if we're going to work through this, what are we asking? We're asking for the probability of getting a temperature drop given, that's what if it rains to me tonight means, given that it rains. So we have our event and we have our condition, which is rain. All right, so how do we calculate that? Well, probability of A and B. Well, what would A and be? That would be it raining and the temperature drop. So where on the Venn diagram do we see that it rains and the temperature drops? We see it right there. That's the intersection of the two groups. So that's 0.1. So there's a 10% chance that both things are going to happen. Now we want to divide that by the probability of B, which in this case is the condition, probability that it rains. So what is the probability that it rains? The probability that it rains is all of the rain information together. So that would be 0.5. So as you work through that, you do your 0.1 divided by your 0.5. And we know that's about 20%. So that's the way we would interpret that. There's a 20% chance that if it rains, then the temperature is going to end up dropping. Okay? So that's just using the formula, treating A and B as separate events. Now we have a two-way diagram problem. So I want you guys to actually try this one out. So pause the video right here, try this out, and tell me what's the probability of randomly selecting a sports car from this group of cars assuming that you must choose a red car. And I'll wait right here. All right, well, hopefully you got an answer that looks like this. Okay, so in the Venn diagram, we can see the condition. So what's the condition in this problem? So if we must choose a red car, so that's the condition. So we want the probability of a sports car, assuming that we're looking at only red cars. So what that tells us is the red row is all the information we need. We don't need anything else. So we can do it by formula, probability of a red sports car, that's the and statement, both A and B occurring. So a red sports car, so that's 0.45, so 45% of the cars were red sports cars, divided by only the red cars. So only 60% of the cars were red cars. So what we end up doing is I can look at it from a formula standpoint, or I can think of it intuitively. If I only want red cars, what's the probability of getting a sports car? So it's this group out of that total. So 0.45 out of 0.60. So if we're only looking at red cars, there's a 75% chance that we're going to select a sports car in that group. All right, so let's move into talking about tree diagrams and how we can kind of put together a lot of these conditional sequences of probabilities. All right, so let's now talk tree diagrams. What is a tree diagram? A tree diagram is used to organize a sequence of events and their corresponding probabilities. So you can see in this problem what we're going to look at is if one thing happens, what follows right after that. If something doesn't happen, what follows then after that. So we get this sequence of events, we get these corresponding probabilities. A tree diagram just kind of helps us organize all of that stuff. So let's kind of talk through this problem and look at how to use a tree diagram to organize all of this information. So here's our example. Shannon hits the snooze bar on her alarm clock on 60% of school days. If she does not hit snooze, there's a 90% probability that she makes it to class on time. Okay, so if she doesn't hit snooze, meaning she gets up on time, then there's a 90% chance that she makes it to class on time. However, if she does hit snooze, meaning she sleeps in, there's only a 70% probability that she makes it to school on time. On a randomly chosen day, so if we were going to just draw a random day out of any possible day on the calendar, what's the probability that Shannon is late to class on that day? So there's a lot of information in here. We're going to use a tree diagram to get it organized and help us calculate this probability in question. So we need to know what comes first out of all of this. You're always going to put your conditions first. So we're going to organize a sequence of events. You're always going to have conditions first. Conditions come first. So what is the condition in this stuff? That's the if. If she hits snooze. If she doesn't hit snooze. If that one thing happens, what follows is going to be the late or on time. So our condition in this case, which is going to come first, is going to be whether or not she hits snooze, correct? All right, whether or not she hits snooze. So what were the two possible outcomes? She could snooze or she could no snooze. That's the condition, and that's the two possible outcomes of that condition. What are the related probabilities? So how often does she hit snooze? Okay, it says Shannon hits the snooze bar on 60% of school days. So she snoozed on 60% of school days. So 0.60. So that means she no snoozed if we use our complement rule. What if we're looking for the opposite or the rest of the probability? 40% of the time. Okay. So she hits her snooze bar 60% of days. She doesn't hit the snooze bar 40% of days. Next, we have the event. So what's the event in this case? The event in question is whether or not she makes it to class on time. All right, so she can snooze bar and be either on time or late, or she could no snooze bar and still come out with the same possibility of on time or late. So now what we've done is we've set up all possible combinations of snoozing and being on time. Now let's look at the conditions. If she does not hit snooze, so she's in the no snooze group, 90% of the time she's on time. So in the no snooze group, she is on time 90% of the time. That means she's late 10% of the time. Okay, late 10% of the time. All right, what's next? If she hits snooze, okay, however, if she hits snooze, so we're here, there's only a 70% that she's on time. All right, so we are 90% on time when she does not hit snooze. We are 70% on time when she does hit snooze. So that means she's late 30% of those days. So we've now filled out every possible combination of hitting snooze and showing up to class on time or not on time, or not hitting snooze and showing up to class on time or not on time. All right, now what do we do with all of this information? Well, what we're going to do is we're going to do what's called the general multiplication rule. In the last lesson, we dealt with or statements. That was the general addition rule. Do we belong to this group or that group? So we added the two groups together. In a tree diagram situation, we're going to use the multiplication rule because we're looking and. She hit snooze and then she ended up late. Or she didn't hit snooze and then she ended up on time. Both things have to happen. So what we end up for general multiplication rule is this formula right here. If I want the probability of A and B, I do the probability of A, so probability of that first event, times probability of B given A. So all this is the conditional probability formula that we used earlier. Remember, we had probability of B given A. What happens to B if A has already happened? Well, what was that formula? Probability of A and B divided by probability that A has already occurred. Well, if I take this formula right here and solve for the and statement, how can we do that? Just using a little algebra. If I want to get rid of divided by probability of A, I just multiply by probability of A. So those cancel out, and what are we left with? The probability of A and B is equal to the probability of A times the probability of B, given that A has already occurred. That's where the general multiplication rule is. It's taking our conditional probability rule and just rearranging that old formula. So it tells us how to deal with ands, how to deal with sequences of events. So do the probability of the first event times the probability of the second event adjusted for any impact the first event has. So that's going to help us figure out how to deal with these, all these combinations that we get here. So let's look and see what we're trying to calculate. All right, so on a randomly chosen day, what's the probability that Shannon is late to class? Probability that Shannon is late to class. Well, there are two different outcomes that end up late, correct? All right, so to be late, she could snooze and end up late, or she could no snooze and still end up late. All right, well, how do we deal with that? Well, we just talked about an and statement. We need to do what with our probabilities? We multiply them together. So we're going to take probability of snooze, that's event A, times the probability that she's late given that she snoozed. So probability that she snoozed times the probability that she was late given that she snoozed. That's all we set up right there. So what we end up with is this rule that when we're dealing with tree diagrams, to calculate a single path, get rid of that, don't need it anymore. To calculate a single path, such as snoozing and ending up late, All you have to do is multiply. Calculate a single path, multiply. So what we need is the 0.60 for snoozing times the 0.30 for being late after snoozing, which is equal to, I think, 0.18. Okay. All right, now let's calculate the probability that she no snoozed and still ended up late. So that's a single path, right? We're starting with snooze and then we're going down here to late. So again, by our multiplication rule, event A is snoozing. What's the probability of snoozing? 40%. So 40% of days she snoozes. Okay. And then times the probability of being late if she snoozed. So times probability of being late if she snoozed, which was the 0.10. So we do the arithmetic on that, we get 0.04. Now how do we deal with that? So I've got two different probabilities here. Probability of snoozing and being late, probability of no snoozing and late. Both of them qualify as being late. So what do we do with those two probabilities? Well, that's what this guy is. We've dealt with this before. What does OR tell us to do? Since both of those meet the condition of being late, both of those would be correct. So we want to just combine those two probabilities. So we know that when we have an OR statement, general addition rule says add them up. And that's the next part of tree diagrams. To calculate a combination of paths, so to combine multiple paths, we do general addition rule. So we're going to add. So I want to combine this first way we can end up late with this second way we can end up late by adding the two together. So 0.22. So what did we find? We found that on 22% of mornings, she ends up late no matter what she does with the snooze bar. That's how we can use a tree diagram to organize something that looks really complex and just turn it into a couple of multiplication problems and then an addition problem. All right, so that's what we're looking at with tree diagrams and general multiplication. Next, I want to talk about this idea of independent events and how we figure out, does one event really influence the probability of another event? So what are independent events? Well, independent events should say that the occurrence of one event does not change the probability of the other event. So these are often confused with mutually exclusive events. Remember, mutually exclusive meant I was selecting an individual and they couldn't belong to the two groups at the same time. This is more about we're doing multiple things and doing one does not change the probability of another occurring. So an example, pretty good example of independent event would be like drawing a card. So drawing cards with replacement. So when we dealt with mutually exclusive, that'd be like drawing a card and saying it can't belong to two different suits at the same time. Independent event says I'm drawing two cards, but I put back the first card before I put back the second card. So that's kind of the difference between the two. Looking for one event, whatever you draw the first time doesn't affect the second event, whatever you draw the second time. That's different than saying, does this fit multiple characteristics or multiple subgroups? So the way we can formula-wise or calculate or determine if things are independent is by just testing whether or not a condition changes the probability. So they're independent if A given B is the same as A. So if A is going to be the same whether or not B actually has occurred, then that means that A and B are independent. Same thing right there. We can flip the order on it. So we're going to work through a problem and test and see if two events are independent. So we have a table here. So we've surveyed about 450 people and we've asked them what's longer, okay? Your ring finger or your index finger, which one is longer on you? And we're going to tie that to the variables male and female and see if one gender has typically a longer ring finger or index finger. So we surveyed a bunch of individuals, and we want to know, are the events female has a longer ring finger independent? We've actually done this before when we were looking for association between two categorical variables. It's the exact same idea, because if there's association, that means that one variable is dependent on the other. If they're independent, meaning ring finger has nothing to do with being female, then there is no association. They're independent of each other. So the ways we check for independence are for association are pretty much the same ways we're going to check for independence. Those are kind of interchangeable ideas there. So we're going to use the formula though and test that one. So are the events female and has a longer ring finger independent? So here's what we're going to do. We want to test the idea for probability of a longer ring finger. Okay. So probability of a longer ring finger. And we're going to look at how that compares to probability of a longer ring finger given that you're female. So that's going to be our two probabilities that we're going to compare to each other. Write that a little better. So our question is, are they equal? If they're equal, then that means being female has nothing to do with whether your ring finger is longer. If they're not equal, that means that imposing a gender on there, imposing female on there, changed the probability of longer ringer or longer ring finger, which means that longer ring finger and female are dependent on each other. Okay. So I'm actually going to pause here, and I want you guys to calculate those two probabilities. Calculate the probability of getting a longer ring finger, and calculate the probability of getting a longer ring finger, assuming that you are female. So pause it here, and I'll wait for you guys to work those two problems out. All right, so hopefully you got an answer. It looks like this. All right, so out of our two answers, probability of longer ring finger, pretty straightforward. 452 individuals, 234 had the longer ring finger, so 234 out of 452. So 52% of our people had a longer ring finger. All right, so longer ring finger given that it's female. So going back to our conditional probability, the condition is female, so only look at the females. So I'm not looking at all 452 individuals anymore. Now it's just the females, 212 of them. And then of the females, how many had a longer ring finger? 82 of them. When we calculate that, 82 out of 212 is about 0.39. So what can we see? The longer ring occurred in 52% of people. The longer ring in the females occurred in only 39% of the females. So we can see that those two are not equal to each other. They're not equal to each other. So something happens when you are a female, according to this, that makes you less likely to have a longer ring finger. So since the subgroup had a different probability than the total group, that means the two are not independent of each other. Okay? So being female does have some type of interaction or some type of role in whether or not you have a longer ring finger. So the way we would write that conclusion is we'd say, therefore, since longer ring finger and since the probability of longer ring finger and the probability of longer ring finger given female are not equal, we can say that longer ring and female are not independent. Or we say they are dependent on each other. Okay, so that's how we test for independence. Look at the one trait in the whole population, then, or in the whole sample, and then look at that trait in one of the subgroups. We could have flipped it and gone the other way. We could have done probability of female, taken just our proportion of females, and then looked at the females who had a longer ring finger. So we could have flipped those probabilities, and we wouldn't have got the same numbers, but we would have got two unequal probabilities there. So it would have just been another piece of evidence. So it doesn't matter which direction we go with that. We would have seen it in both directions. So both of them would have confirmed that longer ring and female are dependent on each other, or are not independent. All right, so that's it for conditional probabilities, independence, and tree diagrams, and I will see you guys in class tomorrow.